Up next, we have Moritz and Willie, and they are going to be talking to us about malware capabilities. So I will let you two kick it off, and if you're new to track 2, I will try to pin all the questions and such to your specific channel, but more importantly in track 2, so it's easy for you to find them.
Awesome. Well, thanks, Heather. And we are just so excited to be here at this event. I mean, the fact that we're able to host this virtually when we're not able to come together in person, so cool the way we're sharing information here. So I'm actually joined with my colleague, sorry, mouse stopped working. There we go again. All right, so here we are. And I'm joined with my colleague Moritz. He's in Germany, I'm in Denver, and virtually we're both in that Discord channel, Ballenthin, Raabe. So as you have questions during our presentation, even afterwards, questions, comments, concerns, ideas, any of those things, shoot on over there and we'll connect directly with you. All right, so I know why you're here. You know why you're here. You're here to learn about Kappa. Kappa is our new open source tool that analyzes a program and identifies the things that it thinks that the program could do. We call these capabilities. And now Kappa uses rules that are written by experts to recognize these capabilities. That means Kappa is expert driven. It's not an AI system. It's not a machine learning system. It's expert driven by these rules, and so it can be easily explained to other human beings, the results. It also has an extensible rule set, which means that Kappa is always learning new capabilities, new things that it might see in malware. Also, you can learn too, because these rules, we've designed them in a way to be easily digestible by a human. So if you're not quite sure how process doppelganging works to effect process injection, you can take a peek at that rule and understand, oh, these are the key features that I would need to notice while inspecting that program. So I know there's a lot of kind of intrepid investigators here with us. You're probably wondering, okay, I understand. Let's see what it looks like in practice. So we're just gonna jump right in. We're gonna take a pop culture malware sample, Wannacry. We saw that spread around the world a couple of years back, and we're just gonna toss it at Kappa and see what happens. Now, Kappa is a command line tool, which means we're going to invoke it from the command line, the terminal. And we'll just run Kappa, point it to our program. We'll see that it analyzes for a couple seconds. It's processing, doing a lot of really hard work, and then it will display those results to us. Let's dig in to what these results actually look like. The primary table has 2 big columns. And on the left-hand side there, these are the capabilities that Kappa has identified in that Wannacry sample. Note that they're nice human-readable kind of fragments of sentences that can help you interpret what this program might do. And as I read through them, I see that this program might be able to send and receive data, connect to a URL with an HTTP request. I see that it can manipulate files on the file system and persist via a Windows service. And as I read through those names, I'm also noticing that they're kind of sorted in such a way that like things show up together. And that makes it easier for me to kind of interpret this kind of page worth of information. Now, another thing that's important to realize as we're taking a peek at this output from Kappa is that Kappa isn't telling us whether or not it's looking at malware. That's not the purpose of the tool. Instead, what Kappa does is it gives us a description of the program that we're inspecting. And we leave it up to you to decide what that means in the context of your investigation. Why I have found this to be sometimes more useful is when I'm dealing with an investigation that deals with grayware. For example, a remote administration tool like Dameware or TeamViewer may be legitimately used by a system administrator to remotely connect to a computer. But I've also been a part of investigations where attackers use the same software maliciously. So that's why this is where Kappa really excels, because it's not going to tell you Dameware is or is not malware. It's going to tell you Dameware is a remote administration tool. Does that fit with your investigation? So as we return our attention to the capabilities identified by Kappa, we find that they do support our current understanding of the Wannacry worm. We see that it has a resource section, and we see that it contains the ability to extract data, including an embedded PE file, and install it for persistence via a Windows service. That's exactly in line with what I remember about Wannacry. I also remember another thing about Wannacry. It always jumps to the forefront of my mind, and that's that kill switch, right? Wannacry, when it first ran, it would see, can I connect to this domain? And sure enough, Kappa is able to identify that this binary connects to a URL. Now, if I'm not quite sure that I trust Kappa here, I can say, hey, please show me your work. And Kappa will not only show us the rules that match the capabilities that it's detected, but it will also show us why it identified a capability. And we see here that Kappa identified the capability connecting to a URL because of the sequence of API calls: internet open URL, internet close handle. That's just what I would expect. And furthermore, it will tell us exactly where in the program this evidence can be found. So for me, as a reverse engineer, this is critical information because now I can go and I can navigate to that part of the program, inspect it myself, and verify that Kappa is working correctly. It's not a magic black box. And so when I open this in IDA Pro and I review the disassembly, what I see is a textbook example of connecting to a URL using the Microsoft API. So that's exactly what Kappa was saying. And furthermore, this leads us to the part of the binary where we actually see the URL that served as that kill switch. So in just a couple moments, we run Kappa, we jump to the interesting part of the binary, and we can extract this IOC and start to feed that back into our investigation. Really neat stuff. So on a whole, I found Kappa to be really useful over the past year as we've been developing this tool. And the key reason why I like it is that it helps me make a decision during an investigation. It's not just saying this is good or bad, it's telling me what I need to care about in the binary. I mean, just think about it. If you're doing an investigation dealing with ransomware, your response is going to be different than dealing with a backdoor that communicates via HTTP. With ransomware, you're probably going to reach for those backups and start restoring systems. You have backups, right? But with an HTTP backdoor, once you realize this, you may pivot to something like the proxy logs as an additional source of information to figure out what the attacker was doing. Kappa will help you with this because it will let you know whether it might be ransomware or an HTTP backdoor. Now, I wrote major parts of Kappa. I know how it works. I know where the warts are inside of the source code. And yet despite that, I'm constantly wowed by how well the tool works. I'm not joking here. I'm really surprised how well it detects some of these capabilities. So I hope you find the same thing. But now that we know a bit about what it looks like when we run it and some of the outputs, let's take a peek and let me tell you a bit about how it came about. Now, me and my team, the Flare team, we're a reverse engineering and intel shop within Mandiant. We spend a lot of time triaging unknown binaries. These might be in support of an investigation, or maybe when we're hunting across VirusTotal, for example, looking for interesting binaries. And usually what we need to do is understand, is this program that we found, does it explain some sort of activity that we know something about? You know, the attacker logged in and they did this thing. Was that affected by this program that we found? And so I'll use tools like IDA Pro and strings and sysinternals and PE parsers. And I'll inspect the binary, I'll extract information, and that helps me make conclusions. You know, for example, with strings, I'll run this tool and it will extract all those human readable bits of information from the binary file. And I use this because in my experience, I've found that a lot of times malware configuration data is stored in this human readable part of the binary program. And so if I go here and I look at the strings, I can oftentimes recover maybe the C2 server address used by the program. So I always do this, even though it's fairly tedious. There might be tens of thousands of lines to kind of wade through. And what really sucks is I have a lot of experience, and so this can go pretty quickly for me. I've done it a lot of times before, and so it's not the end of the world if I have to wade through 10,000 lines because I can do it pretty quickly. But for those without too much experience, this can be a really arduous task. You're not really sure which string am I looking for, which piece of information should I pull together and make a conclusion. That's really hard to do. And so what Kappa is doing, and why we share it with the world now, is that it starts to stitch together a lot of these pieces of information and start suggesting to you next steps. Because we've noticed that a lot of tools, as they exist today, they're technically correct. They give you true data, but they're very conservative. And even if it's easy to suggest the next step of analysis, or even if it's easy, these tools do not go ahead and give you extra context or interpretation. They place that burden on you as the investigator or analyst. So Kappa is our response to this, a tool that can automatically recognize patterns, start to make analytical conclusions, and lead you on a path to get back to your investigation, get back to finding those bad guys and kicking them out of networks. So now that we know a bit about how Kappa can be used, a little bit about what its output looks like, let's turn it over to Moritz, who's going to show us exactly how the magic works behind the scenes.
Awesome. Thank you, Willie. I'm very excited to be here and sharing this tool with the whole community. So I think I have control now. Yeah, perfect. Thank you. So let's dive into how Kappa actually works and automatically identifies capabilities in a program. Doing that, it relies on two main components. First one being a features extraction engine, where we do code analysis to pull out features such as strings, the disassembly of a program and a code flow. And then also a rules engine, which applies logic to find combinations of these features. Let's dive into the features extraction here first. Here we see the general structure of a Windows PE file that contains in some part of it the executing code. In that code, or on that code, we can apply advanced static analysis and reverse engineer the program flow and the disassembly from it. Here's an example code segment disassembled in IDA Pro, and some of these features that are interesting here and that we pull out with the feature engine are API calls, which are present in the binary to tell anything, to allow for any functionality in the program to happen. Then numbers, which are commonly used as constant, being passed to such functions to specify their real behavior, or in programming constructs such as loops or conditional jumps. Then we also pull out things like string references, which allow us to also get more detail about what is happening in this code segment. A very cool thing here is that we can associate all features that we find with the respective offset in the file, so the virtual function offset or just a general file offset. And not only that, we can also associate it with encompassing context. So for example, if we disassemble a whole function, we can group every feature that we find in that function with that specific code part. Even on a lower scope, these disassembled functions normally consist of basic blocks, these little building parts of functions. And for each of these features, we can also associate them with those blocks. Besides the code, we can also pull out other metadata, including header information or other section, such as the import address table, or pull out the strings from the entire file. Most of them we will likely find in the data section. So now that we have all of our features extracted from a binary, we put them into our big features bags, associate them with their respective context if necessary, and then we can start our rule engine. The rules work under the assumption that once a specific combination of features is present, we can deduce that the capability is contained in the file. To illustrate this, let's look at this disassembly segment here again. Normally, when I reverse engineer, I don't look at every instruction line by line. I focus more on the bigger picture and some features that stand out to me. Here in this case, these two API calls in combination really indicate to me that this is some kind of dropper-like behavior where we first write a file to the disk and then execute it using that second API call. Another example, here we see 3 numbers as constants being passed to this socket API call. And if you've done socket programming before, you may recognize that this is the creation of a TCP socket. And as reverse engineering becomes more and more used, or over the years, I learned more of these reverse engineering techniques and tricks and these little patterns. And now I think finally with Kappa, we found a way to codify this knowledge into extendable and repeatable a process and make that accessible to everyone here really in the community. So the bigger picture, we extract our features, we apply a rule logic to it, and then that results in our program capabilities. Since the rules are really the core part of what we do here with the detection and the combination of features, let's dive into how they look like. Here's an example rule. We use the YAML syntax for these rules. You can see they're nicely to understand by humans, easy to read, and they're also good to parse using programming languages. In this rule here, we have 2 main sections. First one being the meta section, which includes the rule name. And that is a unique identifier among the entire rule set, specifying the capability that we're trying to detect here. This name was used in the example output that Willie showed in one of these first slides and indicates the capability. With every rule, we can associate a grouping and categorization to make them easily, to get an easy higher level understanding of what a program is doing based on these different categories. Associated with that, we support other taxonomies to do tagging of behavior in programs. For example, the attack framework to go from an input file and associate this capability with the specific attack technique. Our intelligence team really likes this capability to do automated tagging of a bunch of different binaries in an automated fashion. Last thing I want to point out here in the meta section is this function scope. This scope tells Kappa basically where to look. So in this case, in a function, and we want to see these features that we're going to talk about here next in the scope of a disassembled function. So now let's look at these individual features. They encode the real rule logic and are really the core of this rule. They consist of a logical tree that combines the features that we're looking for using things like and, or, not, and also range counts. And then we have the actual features. And those are really at the core of things I look for when I reverse engineer a sample, looking for specific API calls, looking for numbers, looking for strings. Here in this example, we want to see a call to open up the registry, setting a value in it, and then those values, those numbers, the constants, and the string at the bottom define the specifics of this operation. Overall, this rule looks for the creation of a registry run key and is a very common technique we see in malware, or used to see at least in malware for persistence. Now let's dive into some other rules to see how they work and what all functionality we provide. Here we have the create TCP socket example that I was talking about earlier in that little disassembly snippet, coded up as a rule with this identification of these specific numbers, 6, 1, and 2. And one of these API calls, we can ensure to find the creation of a TCP socket. Here we define the scope of a basic block to really make sure that all of these segments, or all of these features show up in a very tight segment in the program to ensure that this functionality is there. Now, as we were developing this, we quickly found out that it's going to be very useful for us to reference other capabilities that we already defined and found with existing rules in other rules, so we can build capabilities on top of each other. And that's where we implemented this match feature here, where we can just reference all the features that were previously defined. And here in this case, we use it to find functions that create a TCP socket and then perform a call to one of these APIs to connect, indicating to us that this program may be behaving as a TCP client connecting to a remote server. And now we commonly see that when malware speaks out to its sudo command server. Last example I want to show here to mainly point out these 2 bytes, these 2 additional features here, bytes and offsets. Bytes, similar to strings, can be referenced in disassembled functions to indicate things like crypto constants, or here in this case, they are being used as class IDs and interface IDs for COM objects. COM objects are a Microsoft technique to provide different functionality on the operating system. And here in this example, we're trying to identify task scheduling access using these offsets. With the this mechanism creates an object, and the offsets then reference different functionality in those programs. And offsets can also be used to identify register offset structures, memory offsets, and other common techniques we see. Again, we associate that with techniques from the attack framework here to achieve persistence via scheduled task. And also in the meta section, we can include examples, which I think is a very cool way for the community to track samples that contain specific behavior in the real world, given the file name, file hash, and a specific offset. And it also allows us to do, during the development of Kappa, once we tweak our rule engine, once we tweak specific rules, we have regression tests to make sure that all of this functionality still matches even after we made those changes. So currently, Kappa supports 261 rules. Here, there's a rough grouping of them by namespace. And I think it's pretty impressive that we already came up with such a high number, especially because we were mostly focused on writing the core of the framework so far. But of course, as we were reverse engineering malware samples over the last year, we were using Kappa, we were improving the rules, we were adding cool functionality, and already have a good coverage. But I really hope that this number of rules is going to increase significantly. I hope the community is not going to only benefit from this tool by using it, but also can help contribute rules back, come back with ideas to us. Willie's going to talk more about this process. I think our goal is to have half of the people who signed up for the summit register, half of the people who registered for the summit contribute a rule, and I think then we're in really good shape. I'm going to turn it back to Willie now to see more of these rules in action and see the engine in action. And yeah, take it away, Willie.
All right, sweet. Let me just get my clicker going again. Not quite there. All right, here we go. So Moritz has done a great job of walking us, kind of bringing us behind the curtains, showing us how Kappa works. And so with these new details, we can go back and take another peek, or peek at another example and see some of the more advanced features and uses of Kappa. So for this example, again, we're going to take that other part of Wannacry. It'll be the encryptor component, the part that destroys systems. And so we're going to run Kappa from our terminal, pointing it towards the Wannacry encryptor. It's going to process for a couple seconds, not that many, and get us our output. This output, again, breaks down to include both the attack mapping that we can kind of categorize this malware into. So this can be really helpful if we're looking at an unknown binary, maybe understanding where it fits within the attacker life cycle there. Is it part of the initial access or part of achieving its objective? We could potentially use this information for that. And then for the meat of the output is the list of capabilities that Kappa identified. And so as I kind of scan through this list here for the Wannacry encryptor, things that stand out to me include the ability to encrypt via XOR, AES, RSA, RC4, excuse me, as well as the ability to enumerate files on the file system and fetch metadata about those storage devices. That, to me, sounds exactly like what I see in a lot of ransomware and encryptor samples. So this is consistent. In fact, as I was putting together these slides, I was like, yes, that pattern, often when I see it, I immediately think in my mind as a reverse engineer, it's probably ransomware. So I quickly drafted up a Kappa rule that can encode this. You know, it's 10 lines long, it's succinct, and it's easy for other humans to understand. And it's easy for me to share this now with other people. And so I'm saying, when I see encryption, when I see file system enumeration, when I see metadata fetch, maybe that's ransomware. And one of the cool things I want to point out here is we're matching based on namespace here, which means that I don't have to enumerate all the different types of encryption that are out there that I'm looking for in the ransomware. I can rely on there being any sort of encryption in the binary, and other rules are going to pick that up for us. So is this a high quality rule? I'm not quite sure yet. I don't know exactly how it works because I haven't had a chance to run on our test bed that we use to quickly identify the false positive rate. But what I can assure you is that this rule captures the spirit of what we're trying to do with Kappa. We're trying to enable the community to quickly encode these rules. And it gives us an 80-20 solution where it does a really good job on most of the things that we actually encounter in the real world and is easily explainable to other human beings. Now, it's not all roses and butterflies because there are many real world samples out there that have been obfuscated or packed. And Kappa can handle these samples very well. Its code analysis engine is just, it's not advanced enough yet to auto unpack the sample and figure out what's going on. But all is not lost because we spent a lot of effort to ensure that Kappa is not just going to throw a stack trace up or even worse, display misleading data to you. Instead, it's going to do its best to identify these edge cases and suggest to you what you should be doing instead. It's going to lead you down this path of analysis. And so it'll say, hey, I think this file's packed. I'm not seeing the results I would expect for this binary. So therefore, you should try unpacking the sample before rerunning in Kappa. That way, you're less likely to make a mistake in your investigation. Likewise, when Kappa encounters a file type that it doesn't recognize or support, it can give you similar suggestions. Today, Kappa supports analyzing native Windows PE files. And that's just because it's what we typically see in our investigations. It's a majority of what I reverse engineer. That's where my experience lies. So when it sees something like an ELF file, a Mach-O file, or maybe a .NET module, it'll say, hey, I don't know what to do here, but I do know that you as the human might want to use a tool like dnspy to decompile the program, and maybe you should take a peek over there. So it's going to warn you and suggest the next step. And all right, but of course, we have some really big plans for where we want to go with Kappa. The number one thing is to collect a massive rule set that encodes all of the really interesting things that we've seen in malware. And that's not just going to come from Moritz, from me and Moritz. That's going to come from the community as well as we kind of look across globally what we see out there and figure out what to recognize. But more on this in a moment. In the meantime, I think there's a natural fit for what we've done with Kappa on a static analysis side and applying that to dynamic analysis. Taking, for example, a sandbox data, like an API trace, when malware was run within a virtual machine and all of its activities were recorded, it seems to me that we could use a lot of the same logic from the existing Kappa engine to kind of map out what was a program doing at any point in time. We might be able to say, definitively, this program, when it first started, it connected to a C2 server. Here are the events. Then it downloaded another payload. Here are the events that support that conclusion. And then finally, we injected to a third process. And we can actually point to the different events that allow us to make that conclusion. So that seems like a natural fit. And then, of course, we're going to continue with our integration with existing reverse engineering workflows so that Kappa can be both useful to incident responders who need a standalone tool to get their results, as well as hardcore reverse engineers who are down into their weeds of disassembly trying to figure out what programs are doing. So we'll integrate with tools like Ghidra, Radare, Binary Ninja, etc. And today, my favorite way to use Kappa is actually within our IDA Pro integration and plugin. And this integration just made a lot of sense because us reverse engineers, IDA Pro is our primary place that we spend time. It's where we explore a file, it's where we save our notes, and it's how we communicate with other reverse engineers. And so pulling Kappa into this workflow is just, it's the obvious thing to do, really. And the way that it helps me do a better job, honestly, it really does, is that it can point and guide me towards the interesting parts of our program. This matters when I open up a potentially malicious file, and I might have 2, 5, or 10,000 functions. I might potentially have to go through a majority or all of those functions to figure out where the key part of the binary is that lets me find artifacts or indicators. But with Kappa, this tool can highlight for us exactly where different functionality is implemented. So when I use Kappa with IDA Pro, I can immediately jump to, for example, the function that constructs the network packet that communicates with a C2 server and allows me to maybe write a decoder or something like that. It allows me to zero in very quickly on the important parts of the program. Another thing I really love about this integration is that the plugin is extremely interactive. And this jives really well with IDA Pro. IDA Pro, the interactive disassembler, that's in the name of this tool. Our plugin is also extremely interactive. As we explore the results, as we review the evidence in the artifact tree, we can easily hyperlink around the binary, and we can select and highlight the entries and addresses that support these conclusions. So I can both find interesting parts of the binary and also learn about patterns that I should be recognizing on my own. It's just a great enhancement to my existing workflow. So at this point, you're probably thinking, where can I get this thing and how can I start using it? Well, I promise you, by the time we get off this presentation, what's that, like 5 minutes from now, 4 minutes, you could have the tool and you could have already run it. Because you need to go to GitHub, FireEye, Kappa, and you can download the standalone executables and run them right now. They don't require any installation, and they'll work on Windows, Linux, and Mac OS systems. So go ahead, download them, give them a try, get a sense for what Kappa can detect today. We'll also be working to get this released as part of the Flare VM and Remnux distributions so that your analysis workstations are pre-populated with this tool. But we don't want you to just download Kappa. What we want you to be doing is to be constantly thinking while you're doing an investigation, while you're looking at an unknown binary, how are you making your analytical conclusions? What pieces of evidence make you think a program connects via HTTP, injects code, or does some other functionality? And can you encode that as a Kappa rule? Because when we as a community encode these rules and share them, what we're doing is we're magnifying and we're reflecting our experience back out globally. We're hoping a couple hundred people might use Kappa. Realistically, a few thousand people, or even, ideally, 10,000 people might use Kappa. So if you're able to express an analytical conclusion with this tool, then that many people just automatically benefit from your experience. We think that would be just so amazing. And that's why we've made it extremely easy to encode your rules, to share them with us, because we understand it's the quality of the rules that are going to make or break Kappa. The more interesting things we can teach Kappa how to recognize, the more useful it's going to be for you all. So, in summary, Kappa is a tool that will process programs and make guesses at what it thinks those programs can do. It'll try to find those capabilities. And it's going to use rules to do this, and those rules can be written by you. They should be written by you. And very soon we'll have a corpus of rules that can identify all the most interesting behaviors that we've actually seen in real-world malware. So at this point, I want to thank you for your time. Please go ahead and shoot any questions for us into those chat channels, and we'll do our best to address them right now. Thank you.